Okay, so I'm going to talk about statistical monitoring of clinical trials, but I think for most of the materials, it has been sort of mentioned in other talks and presentations. So I think so the way I would view it is sort of a capsule or some sort of reorganization of the material so the material presented in a different perspective. So some of those you've seen before in this. In these few days already, but so this monitoring is sort of a broad topic, and I try to narrow down to more specifics about the type of monitoring that we're going to do. Efficacy. So the three types is statistical efficacy, futility, and sample re-estimation. So again, these are the topics I've seen before. So and this is a small group enough that I realize this is better to interact than just me like talking one way direction. So if you have any questions, comments, feel free to just say. Overview and the traditional role of statistician in clinical trials is day one of a meeting, your clinical collaborator comes to your office, say what's sample size, and then if you're good, you manage to come with ask the right questions, get the right answer, and then 5 years later they come back with the test and say, oh, let's do a t-test. And so that's the traditional role, right? So but what happened during this 5-year period? Obviously, the clinical investigator will actually monitor the trial actively. And so the question for us is, what is there any contribution that statistician can do? So in my opinion, there are many ways that like statistician can contribute to this process. And the best way to do it is to plan ahead. So for all this monitoring, we can do something ad hoc or like in the context of DSMB that when you see data, you do something creatively. But I think that the best approach to it is to think in advance of time and plan for it. And so that's really two ways we can think about it. The reason for doing this is to avoid biases, because sometimes when we don't want to stop early for efficacy, obviously we can't do it and whenever we want to after we look at data. So we want to avoid bias. So this is sort of a way to uphold scientific integrity. This is what I call like the policing part of statisticians. So like a statistician would say, no, we can't look at the data and say and do this kind of stopping. And so this is important part to uphold the scientific integrity of the study finding. The more positive side of it is that but if you plan the monitoring schedule and timing and rules in an efficient way, you actually improve the efficiency of the study. So we actually can contribute in a way that makes everyone happy, but avoiding bias is important. So one of the most preferred form of monitoring is early stopping. I know some people don't like the term because we don't stop the trial early. We stop the trial at the right time. We never stop the trial early. But the proper way to say is that we stop the trial earlier than planned. But for the sake of not like saying too many words, I was just say early stopping anyway during this presentation, knowing that it's on record. But to clarify this, what I mean is we want to start a trial earlier than planned for several reasons, right? And these are sort of the 4 reasons that I can think of. If you can think of any other, I'd be happy to update my notes. So this is I'm going to bring it back to my class in 4. So if your opinion, I'll acknowledge your contribution to the class. And the first type is risk monitoring. So this is obviously important safety monitoring. The way to go about it usually is that like if your DSMB meets every 6 months or so before the DSMB, the blind statistician will prepare the report and then sort of list the AE of the treatment labels and then you probably want to do some sort of like high-square test to monitor whether there's elevated risk in certain arms. So this is this should be done obviously, but there's not much planning about it, especially for like AE that you don't expect, right? For certain type of AE that you expect, you probably want to have a specified monitoring rule in the protocol. For example, if a drug that you think will likely cause hypotension, and you want that to be pre-specified. the risk monitoring, in my opinion, is sort of one thing that you have to do and present it to DSMB, and they need to deliver on the evidence. So not much planning in this sense, so I'm not going to talk too much about it, but this is something that we have to do. The second type of stopping is stopping for efficacy. It's obvious that if as the trial progresses, if evidence shows that the treatment is better than the placebo or the standard of care, we should stop, so that we stop treating patients at the placebo arm. And for this reason, stopping boundary should be two-sided for efficacy, because not because we want to market the placebo after demonstrating that placebo is better than the treatment, but because of the reason that we want to stop giving a drug that is inferior to placebo when we have enough information. So stopping for efficacy, you always want to have a two-sided boundary. The third reason is to stop for futility. It's an opposite reason for stopping. This is usually not a happy reason to stop, meaning that you basically want to stop the trial and say that it's a negative finding, but this is good in the sense that you can redirect all the resources to other potential trials. So this is the third reason. So I'm going to talk a little more about how to come up with boundaries for stopping for efficacy and stopping for futility in my presentation later. And the fourth type of stopping is due to external evidence. This is totally out of control. So your trial is running well, everything is well executed, and then there's a new drug in the market that basically makes the drug you're testing irrelevant. So then you may want to stop the trial. This is the decision point will be decided by DSMB and other more external body. And another possible reason for stopping the trial early for external evidence is that if there are other trials of the similar drug that show side effects to the drug, you probably want to stop for it, even though you may not see anything like this. So one of the trials that I've served as a statistician is using Statistical in ALS patient, and then we use a two-stage design where we enroll patient in the first stage, and by the time we do the interim analysis, there was some new evidence showing that psychosis is actually some side effects, and so the investigator talking maybe there'll be reason for stopping the trial early, and as it turned out, we sort of lucked out in the trial at the interim analysis. The other arm actually is shown to be better than Statistical, and we managed to stop the trial early for efficacy. At the same time, the external evidence showed that, well, we may want to think about stopping the trial early because we have evidence that Statistical may be causing elevated adverse events. But again, this is something that's out of control, nothing that we can plan about, but this is something that we want to be having an open mind to as a statistician. And so early stopping is one big class of monitoring things that we can do. The other type of monitoring is to do sample size readjustment. So early stopping is like you plan a big N and then you stop early. The way I view sample size adaptation is that you plan a small N at the beginning, use the information to expand the study so that you have adequate power at the end of the study. Right? So this is sort of a reverse way of doing monitoring. I'm going to spend some time on how to do that as well. And then the last type of monitoring is really what I call the kitchen sink. It has everything in it. You can drop a loser, play the winner, enrich the population, change the endpoint. So there are many adaptations you can do, but this is just a broad topic that requires a lot of specialization. Also about to tailor for each specific trial, so I'm not going to talk about that because the goal I think for this is to give you some basic tools and concepts so that you can at least do the basic stuff. For the more creative stuff, it'll be fun, but it's out of scope. So yeah, if you are teaching my class, I would say that would be good for class project. But you guys have a lot of projects that you can afford to take on more. The beta blocker heart attack trial. It is probably one of the earliest clinical trials that use the stopping boundary for early stopping consideration. So it was conducted in the late 70s or early 80s, and under the corollary drug project. And so in this phase 3 study, we're comparing a great blocker versus the placebo in post-heart attack patients and endpoint mortality. And the planned statistical analysis was the log-rank test to sample survival, and very straightforward. But the study investigators and the DSMB used the O'Brien-Fleming stopping boundary as a way to monitor for efficacy, and they also supplement the stopping boundary with conditional probability. So you see that when we do monitoring in practice, we want to have something that's planned, like in this case the O'Brien-Fleming stopping boundary, but we sometimes will supplement what the planned analysis with something that's sort of ad hoc, which is conditional probability, just to give us evidence and show it from another angle. But let me show you, this is the trajectory of the data. So the enrollment started in June 1978, and the study has 7 planned analyses, including the final analysis. So indicated by the solid line there. So there are 7 points on the line that indicate the timing and the criteria for stopping. And so if you're familiar with O'Brien-Fleming, we are very conservative at the beginning. So at the first interim, unless you see it, some sort of disaster in one of the arms, you need to stop when the Z value is over 5. So this is pretty high bar. And as the trial progresses, the threshold sort of went down to something that we would expect. And the final analysis, the critical value is 2.0639. So this is sort of the stopping boundary defined by the O'Brien-Fleming method, and the dots without the not connected are the actual observations. So at the first interim analysis, they calculated the Z value based on log-rank test of 1.68, which is, so by the way, so I just show half of the boundary. So Z value is calculated in a way that, so when it's positive, it's favorable to the treatment. So that's an symmetric boundary about the 0 line, but I'm not showing that. So there's some indication that the treatment is working, but it's way below the threshold, and then the Z value was updated every interim analysis was pretty constant, around between 2.2 and 2.3, and at the 6th interim analysis, the Z value was 2.62, that crossed the boundary. And this is a point that triggered the consideration of stopping for efficacy. So again, there are 7 planned analysis, and the decision was made was deliberated at the time that all patients have been enrolled and treated. So basically, all that remains is follow-up. So that one of the practical considerations here is that, well, I mean, everyone is getting drug and do want to stop at this point. So this is a practical consideration. But what happened is, well, it's good to have a DSMB that make all the decisions that and give some clarity to the issue. And first of all, because of the fact that the observed Z value crossed the stopping boundary, there's a justification for why we want to stop. And the evidence is augmented by the calculation of conditional power. And based on conditional power, and I'm going to talk a little bit about conditional power in the context later. So the DSMB decided to stop the study and for efficacy. And so that so they publish the result and say that, well, this beta blocker is something that we want to do. So this is an interesting example, which is illustrative of a few points that I'd like to sort of extend to get some more general principle. The first one is the obvious thing is why not 1.96? The adjusted p-value. This is so. Hopefully, this is something that that's trivial to you, and you say, you roll your eyes and say, why do I need to say that? But I just want to make sure that we all understand that why need to not to do 1.96. So why not 1.96? The second is how to use a stopping boundary. The third point is how to build a stopping boundary using our experimental function. So these are 3 points. Why not do that? How to use it and how to create it. Obvious reason, at least in the context phase 3 study, we have a very strict control of false positive error, which is called type 1 error rate, and we don't want to say drug that doesn't works. So if we use 1.96, we're going to have inflated type 1 error because by the virtue of looking at the data multiple times, and whenever we win, we just say we win, and then we forget about the occasion that it doesn't win. So if we look at the data at one point of obvious type 1 errors will be kept at 5%. But if you look at the data twice, one intermediate analysis before the final analysis, type 1 error will be about 80%. In the beta blocker part of the test study, with seven analysis, the type 1 error would have been around 1.5 if we were using 1.96. So that's the reason why we do want to adjust. We don't want to use 1.96. So the obvious way to adjust for to control for type 1 error is that to change the threshold, right? Instead of stopping when the Z reach 1.96, we want to have a higher bar. So this is the motivation for the first stopping boundary by Pocock in the 70s. And so if we have 5 analyses planned at equal space, then in order to keep the overall type 1 error at 5%, the correct predicted value should be 2.413, meaning that at the end of the study, if you get a Z value of 2, you will not be able to reject it. So this is I think one of the reasons why people don't like the Pocock, because you've got to be really conservative at final analysis. You want to be able to reject your null hypothesis when Z value is about 2. So it is high bar. And for that reason, people tend to use the O'Brien-Fleming. Actually, in all the phase 3 trial that I've seen that has a early stopping rule for efficacy, I have not seen one that is not using O'Brien-Fleming. And the reason is, it's again very conservative at the beginning, so that we have some alpha left at the final analysis. And using the same example with 5 analyses, including the final one, the Q value at each point will be from 4.5 down to 2.040. So, and then the critical values will change depending on the number of analyses you do. Generally, if you have 4 analyses, your critical value at each time point will be higher. And for this reason, so one of the practical considerations is how many analyses we want to plan and the phase 3 study for efficacy. And for this reason, we use O'Brien-Fleming, but with equal spacing of the interim analysis. I actually don't like 5 because of the fact that the final critical value is about 2. We want to reach, and 5 it seems to me is a lot, and I usually like to use 3 or 4, so that at the end, the final analysis, if you get a Z value of 2, you'll be able to reach it. So this is sort of my rule of thumb. As arbitrary or as like why we reject the null hypothesis at 5%, I don't know, but this is sort of the way that I like to do it. But it's not wrong if you have like 7. They did it in the 80s. So this is O'Brien-Fleming, and the fun part about stopping boundaries is that you can draw whatever shape you want to do as long as you abide by the rule, right? So Pito had this really interesting looking boundary back at the interim analysis, but calculation showed that at the final analysis, they deliberately have control at 2. If you look at the dot, the final, and so the way to create this boundary is that you first decide like 2 at the final analysis, and then you determine the critical value required for the interim. So this is sort of a backward reverse engineer to see what the alpha you want to spend at the interim analysis. Yeah, I like this idea, but I've never seen this used.
Just if you don't mind us trying to get.
Sure, yeah.
So that question about how many analyses to do, I agree with you, but sometimes I know you have the discussion with the clinician and they hear, oh, you can do frequent interim analyses. So So we showed them the probability of stopping if you add on more. But usually once you do past 4 or 5, the probability of stopping at each interim look, it's not worth the inflation and the alpha. So just something to think about when you have that discussion.
Right, yeah, so I definitely agree with you, and it's good to really run some number to show them that, because it's sort of counterintuitive, right? So I think this is why I say that avoiding bias is one of the jobs of statistician, and the intuition is that everyone wants to stop the trial early for efficacy, but we also want to stop, because we want to see a potential win, we want to just snatch it, right? We don't want to let it slip away. So the intuition is that if we look more often, we will reject more often. But what they need to know is that if we look more often, the criteria for a win is higher. So it's sort of in a way washed out, and so the practical way I like to do interim analysis without doing actual calculation is I like 3. I like to have one plan really early on to make sure that there's no disaster, everything is properly run, and then there's another one at 2/3 of the time point. Because if you have an interim analysis that's really planned at the late stage, really you're not changing how you have treated patients anyway. So what you really gain is like you release the result earlier, benefiting potential future patients. But again, that can be deliberated from the DSMB, and this is sort of related to the next step, the next slide I'd like to talk about. So these boundaries, we know how to use it, right? Because we have the boundaries, we just look at the boundary, look at observation, and then whenever the observed z-value cross the boundary, you stop. That's easy. But these boundaries assume that we have equal spacing. And then we also talk, yesterday there was also a discussion on if we do a sample size estimation, do we change like when we do the analysis? And but by having pre-specified boundary is good. This is what we like as statistician. But what is not good is that it gives us it put us in a box that we don't necessarily be in, and we do want to have some flexibility, and that's where alpha spending function comes in. So again, drawbacks of having a pre-specified boundaries is that we need to determine the number of interim analysis at the beginning. In a sense, I think it's good to have to know the interim analysis, but the bigger problem is that the timing of the interim analysis has to be determined at the beginning of the study in terms of the information fraction, not in terms of calendar time. But if you think about like scheduling like busy people to serve on DSMB to review the data, you want to do it like on calendar time, right? So and like every 6 months, but you cannot control recruitment. So maybe in the first 6 months, you have not reached the right number of information that will trigger an interim analysis, but you want to meet anyway. So controlling the timing of interim analysis can be tricky based on information time. So you do want to have some flexibility in that regard, and that's where alpha spending function comes in. So the idea is that to specify the amount of alpha you want to spend at each interim time point, expressed in terms of information fraction. Information fraction is just a sort of measure of how much information you have at that time point relative to what you would have at the end of the study. Usually it is a ratio of the sample size. So for example, if you plan the study to have a maximum sample size of 100, if you at the interim analysis you have 30 subjects, so the information fraction will be 1/3. So this is one way to calculate information fraction if you have a continuous endpoint. If you have a survival endpoint, then you define the information fraction by the number of events that you see, and relative to the number of events that you expect to see. But assuming that you know how to calculate information fraction at calendar time of the interim analysis, you can. So the beauty of alpha spending function is that you don't need to. You can really draw something somewhat arbitrarily, and then that will be a valid design as long as the information fraction one, the cumulative alpha, which is the vertical axis, is the type of area that you like to control. So in this case 1.25 because it's one-sided, but there should be only one side. So as you can see, so these are the two alpha spending functions that mimics the O'Brien-Fleming and the Pocock. And for the Pocock, alpha spending function, you see that at the first interim we spend a lot of alpha, so about 0.0075, and then at each interim the amount of alpha that we spend is roughly uniform across the information fraction timescale. Whereas the O'Brien-Fleming, we are very conservative, we spend very little alpha, almost zero at the first interim, and then so that we can have a huge alpha jump from point A to 1, so that's the amount of alpha that we can spend according to O'Brien-Fleming boundary. So, so the good thing about alpha standard function is that we have dots on the information fraction, right? But in case that in the implementation of the study, instead of doing a interim analysis as like a 0.4 information fraction, you are doing an analysis of 0.5 at 0.5. You could still use the alpha standard function to determine the critical value that you will need at that particular time point, so that you are not boxed into the five analysis of 0.2, 0.4, 0.6, 0.8, and 1. So you could actually change the calendar, the critical value based on the calendar time that you want to meet as a percentage.
So do you just then use whatever information fraction you have, go on the function and just use that critical value?
Yeah.
I mean, just
Yeah. So you do need to know how to calculate this, right? So and that's the moment I realized I'm talking to a bunch of statisticians, and thanks Jeff for showing up, and I added this formula, so just to so but yeah, good appreciate. So this is the slide to show you how to calculate the critical value at each time point. I like to do my own stuff, but they're actually software out to do it, so you don't have to do it yourself. But this slide is to demonstrate what information you need in order for you to determine the critical value at each time point. So the way to calculate the critical value at an interim analysis TK, time K for each one. So the critical value is CK, right? So that value will depend on the critical values you used in the previous interim analysis. And then the cumulative alpha that's allowed by your alpha spending function. So which is the difference of the alpha at the current time point and the alpha at the previous interim analysis. So as you can see, if you're doing two interim analysis at very close proximity, the amount of alpha you can spend will be very small, meaning that your critical value will be really large. So the one intuition is that you think, we are close to the boundary. We're close to the critical value at the current analysis. Maybe if you look after like the next patient, we will actually go across the border. That's not true, because the alpha you can spend between the two time points is so big that no observation will make you go across the boundary. So the intuition here is that first, from a statistical point, you need to know what information you need to calculate the critical value, which is the critical values from previous analysis, and the alpha based on alpha spending function you specify. So one thing about alpha spending function is that if you design it at the planning stage of the study, you keep it. But however you want to use it, when you want to use it, it's all flexible. So that's a good thing about having alpha spending function. But you need to know that you don't want to use it too often, right? Because you'll be counterproductive. And so this is my formula. I won't formulate the talk. So let me see what else. So this is something that I think I've gone through. Useful to So while flexibility is a double-edged sword, it's good and it gives you some comfort. But you do want to plan, even though you know have some flexibility. So the way I would do a study with software for efficacy is that I'll present the operating characteristics based on O'Brien-Fleming of boundary with pre-specified time point anyway. So that's something that you want to show, like what's the power of early stopping and what's the power and whatnot. So this is this is good, doesn't mean that you cannot change that, but it means that you are thoughtful about the process. And yeah, so.
Then do you just say that if something's off, you might use or you just present the alpha spending function using kind of the general O'Brien-Fleming rules?
Right, so yeah, so I think alpha spending function allows you to change the time of the interim analysis, but I don't think this is a good idea. It allows you to, for example, you plan at like 1/3, 2/3, and then the final analysis. I think it's okay if you do the first analysis at like 0.4 information function, but you don't want to have a drastic change, right? So
deviate from what you had planned.
yeah, so the idea is that so what actually will happen will not deviate from what you planned. So, but so I think the point of flexibility is that we don't want to be like no you can't, like statistician one thing is that no you can't do it. We say we are going to do it, you can't change the plan. This is so alpha spending function is a tool for us to be more flexible, to be more human, I guess. Machine, right? And so but that is not a license for us to like do something that we don't set up. Again, this is just me. It's sort of personal opinion, and
I agree with that because we use it, and I think it's helpful because unfortunately a lot of times the DSMB does say, oh, add another look. So that happened a lot of times because of this. They're might be seeing something, and they say, "Well, we want to take another look."
Yeah.
So this kind of allows you to do that.
It helps prepare just in case the DSMB wants that.
Yeah, and the way to respond to that, I've done that once before, and then I'll just show them. Well, if you do it, I just come up with some hypothetical scenario to show that it's actually counterproductive. You want to do it. If reading the mind that they want to call a win early, so show them that this is not what you want. So, yeah, but good. Thanks.
Like you give them the figure so they can actually see how the critical boundaries might actually change.
Right.
Like what they're probably expecting.
Right, because you can calculate the critical value if you do the next interim analysis tomorrow, so that would be your critical value. It's so big. And then of course they say, why it doesn't make sense, why it's so big? Then this is a different story. You need to explain it and exercise your communication skill to understand. But this is an interesting process. It sounds awful, but actually I enjoy the process a lot. Okay, so let's move on to starting futility. The concept is very similar. So I'm going to not to touch on anything that's technical. The idea is that the outer boundaries are stopping for efficacy. So if the observation cross the black lines, and we stop and call for a win. And then analogously, if we want to receive data that suggests that there's no way that we're going to cross the black line, we want to stop the study, and that's one way to do it is to come up with what we call futility boundary, indicated by the red line. So this is sort of a great example that the dots show the observed data as we progress, and for interim analysis, we did the red line, and then we stop the trial, and then say that it's futile to move forward. So let's stop and save some money.
So earlier this week, we heard the suggestion that if we have a 2-arm trial versus placebo, that these boundaries should not be two-sided, because we wouldn't want to continue in order to show that placebo is better than sleep-holding, or whatever your active treatment is. But earlier today, you mentioned a two-sided boundary. So, can you just comment on that? Because you could set it up one-sided at 0.025 for efficacy and have the futility boundary basically cover the case where placebo is better.
Right.
What are your thoughts on that?
Oh, so you mean why? Yeah, so I think my comment was on the stopping boundaries for efficacy. I like to have it two-sided. And the reason is not that we want to get a placebo approved for marketing, but it's because of the fact that if the observation cross the bottom solid line, we know that the treatment, Statistical in this case, is inferior, and we don't want to put patients on statistical, and this is more ethical
Right.
consideration.
But if you had a one-sided efficacy boundary, you
Mhm.
could do a one-sided utility boundary, right? So if
Right.
you were unable to show that the active treatment is better than placebo, then you would stop for futility.
So basically, if I understand it, what you're saying is I can use the second bottom one,
Right.
O'Brien Fleming, as the futility boundary.
No, so
No.
the bottom one wouldn't exist.
Okay.
Right.
And the futility boundary would basically go,
Top red line?
it would,
Top
it
red
would
line down
differ a
first,
little
yeah.
bit, but yeah, you would have a red line that goes and covers everything below.
Right.
And the
Another
reason
way
I-
to say it is that the futility boundary, you can never hit the lower efficacy boundary. You always hit the futility boundary
Before,
first.
right.
So it's meaningless to say you have a two-sided efficacy boundary when you have a futility.
I see. So yeah, I think that's an interesting thought. I should know. I guess. My intuition is that it may actually affect the power in the following sense. Because in the context of phase 3 study, a futility boundary is non-binding in the sense that you don't want to design your efficacy boundary based on the futility boundary, right? So and that result and because we know that stopping for futility will not increase your terminality, so we're okay with FDA and as a result of that, it may decrease the power slightly little bit. What my suspicion is that if you don't have the lower efficacy boundary, but in order to prevent when in case that the placebo is doing much better than the treatment, my suspicion is that we need to have futility boundary that is so liberal that you stop the trial much earlier for futility than we like. So and as a result of that, we may actually decrease the study power. This is my suspicion. So
So I'm asking because we had a study where the we had a two-sided efficacy boundary versus placebo, and
Yeah.
the DSMB stopped us based on conditional power. We actually had quite good power to show that placebo would be better at the end.
Yeah.
But they said that's ridiculous. We're not going to continue the study to be able to conclude that
Right.
definitively. And so at that point, of course, everybody started to say, well, that should have been one-sided. We all should have caught that from the beginning.
Right. So yeah. So this may be a good exercise to see whether my intuition is correct. That if we do a one-sided efficacy, but we have a futility boundary that will call for stopping earlier than we issued, then it may actually decrease the power. I think that's an interesting.
I think if the one-sided is at 0.025 level rather than 0.05, that addresses part of the power concern.
Right.
And yes, you will stop earlier for futility
Right.
than for failure on efficacy, but that's why you have futility data, because you want to stop earlier for futility, so.
You're right. Yeah. I think that there's some confusion on that. But when my practice, I never specify futility boundary. I like the concept of conditional power better actually. Yeah, because it's very it's in a sense it's ad hoc, right? But it's not ad hoc in the sense that in my study I like to specify conditional when I do conditional power and how I'm going to do it. Right? Because you calculate conditional power, you need to make certain assumption whether you condition on the current trajectory or you condition on the null value, condition on the alternative value, or you want to do some sort of Bayesian thing to average under different scenarios. So whatever method you use is fine as long as you specify in the protocol how you will do it. So I think, and it's much more intuitive because when we talk about boundary, it's good to have some clarity, but then you box us into something that might not be necessary, right? But it's interesting. I need to think more about like the one-sided efficacy.
So for futility, you are using beta spending function.
Yeah, so you could use, so that's a corresponding method to come up with a boundary or beta spending function, which is interesting idea. I don't like it because actually it requires some assumption. In order to create the futility boundary, you do need to have some assumption made, unlike the efficacy, the stopping boundary for efficacy that all assumption you need to make is under the null, which is always zero difference, right? So that's the reason why I like to use conditional power as a way to to make interim decision for whether we want to stop a study early for fertility. Yeah, but
Can we use conditional power?
Yeah.
And I agree with you, you have to say which assumption you're calculating it under, but I've used it in my studies as well, and when it comes to presenting it, whichever assumption the DSMB agrees on, I find it hard, that threshold. Like the DSMB can't, it's a hard time pre-specifying, okay, my conditional power is less than 20%, then I'm gonna stop the study. But if you're saying that and you're 3/4 halfway through the study, I feel like 20% is a pretty low bar. So do you have any recommendations for setting that threshold? Because it would be nice to set it before they see the conditional power. But a lot of times there's just a discussion in the DSMB and everyone's like, well, what should we do?
Well, this is there's no rule. I like 10% or lower actually. 20% sounds, so the intuition is that like you first set up the infrastructure for running a trial, and then you are like 4/5 of the chances like for it and like enroll all the subjects. You just follow up patients, and unless you this is really like there's no chance that you're going to see a difference. You want to go. So I tend to be a little bit conservative in this sense of like not to call for early stopping due to fertility. Yeah, but I mean, this is my number, but this isn't. But no matter what number you choose, you probably want to back it up with some plan simulation to show what the operating characteristic is. And again, the simulation is done at a planned time point, and but in the actual study, the time between conditional power may be slightly off, but that's fine. I think you should not be off that by that much. Yeah, so I don't know whether like if you try other numbers, so.
For the simulation,
Yeah.
to see
Oh
what.
no, how you communicate with the DSMB about, or
It's-
what they decided at the end.
Most of them decide 20% because I think they saw it in the textbook somewhere. They're like, oh,
There's
that
a
threshold should be
textbook.
20%. But then I asked them, I said, well, if we're going to do, because sometimes they'll look at it and then they say, you know what, we want to add a conditional power. So let's look at like we say we're going to look at it a third of the way through. They look at it, then the DSMB says, maybe we'll keep going, but can you show it to us 2/3 of the way through? So it's like they add another analysis.
Yeah.
I mean, you don't take a penalty on that, right? I mean, you're just, or do you?
I think there's a little penalty, but I've never quantified it.
Right. So the penalty is in terms of the power, right? I guess the decision is to stop and call it that you don't win. So and it doesn't. You don't get penalized for invading time and error, right? But the more you look in this case, will actually be not as good as to the investigator, right? Because the more you look, the chances of false negative will increase, and so you will definitely decrease actual power. And I try to be loose on this, like stopping for fertility, because I think there are also other information you want to take in, secondary endpoints, right? Because and so you may not win on the primary endpoint, but there may be some indication that warrant further study on the secondary endpoint. So this. I like, as a statistician, I like to have a primary endpoint and primary analysis so that we know that we're going in to get something with certainty, with certain accuracy or likelihood. But I think we should not only do this based on one endpoint, right? So and then the stopping for fertility is where I think give us some leeway to deliver the evidence in totality instead of just we cross boundary, so stop, we cross boundary beforehand. So and they need us in this next place. And but I think but this is where clinical trials get interesting, I think. And one clarification. So you've heard of fertility design. So this is a very confusing terminology in our community. So that we use fertility for two different ways. So in fertility design, your goal is to prove that a drug is futile for further investigation. So when you stop, when at the end of the study you do an analysis, you make a definitive statement. In the context of stopping for fertility, you stop and without a conclusion. Basically, it's a stopping for inconclusiveness. Basically, stop because you know that there's a low likelihood of making any definitive statement. So you're not stopping for negative result, you're stopping for conclusiveness. So there's a slight subtle difference, and in the context of the entire program, futility design is usually used in the early phase, and the futility parameter that I mentioned here is usually something that at the phase 3 trial. So there should be no ambiguity, but just in case that you mentioned futility, some precision. And speaking of that, futility interim analysis, in my opinion, is very useful in early phase studies and not only in phase 3. And Simon two-stage design, this number will not be Simon two-stage, but two-stage design is one useful way to screen agents in early phase. So this is what the two-stage design looks like. You instead of enrolling like patient all the way to the end, you start the trial with a small batch of subjects, in this case 20, and do an interim analysis where they want to continue after the 20 subjects. So the rule here is that after the first 20 subjects, if you have less than 6 responders, then we stop. That's concluding that there's no, the likelihood of having a positive result will be low. So that's not concluding futility. That's basically saying that it's not promising to go forward. Although from a no-go decision, the implications are good. And then after that, if after the interim analysis, if we have more than 6 responders, we expand the cohort to under 51, making it a 71 subject study. So this is two-stage design. Everything is the numbers in red underlined should be re-specified based on the typical like how capital incidence stuff like 5% Taiwan error, 80% power, you could change the number a little bit, could be 10% Taiwan error in the early phase. But these are the numbers that you ought to specify in the protocol when you plan the study. And the obvious reason for stopping early for futility is that we can save a lot of money and resources, and we direct our resources to other drugs and compounds. So for this particular design, under the note that if the response rate is 25%, which is a sort of low response rate, there's 60% chance that you can use a simple calculation. There's 60% probability that the trial will end with 20 subjects. So this is the main motivation for doing a futility interim analysis, right? Because you stop the trial early and move on to something else. So it's good for screening. And in comparison, if you don't have this interim analysis, you just want to do a fixed sample size single arm study under the same Taiwan error and power constraint, you need 62 subjects. So one simple observation, 20 is less than 62. So that's why we want to do it, right? Second observation, if you remember, in the two-stage design, total sample size can go up to 71. Observation number 2, 71 is greater than 62. Now, you see the trade-off, right? So having an interim analysis will increase your maximum sample size. And so this is one of the things that you probably want to articulate well to your investigator. And in this particular case, if you're doing a single-arm two-stage study with this interim analysis, there are 2 scenarios for the investigator. You can stop the trial early if your drug doesn't work. That's bad, right, in a sense. Or if your drug does work, you need 71 instead of 62. And then so you see that there's really no huge incentive for the investigator to do this design compared to the 62 fixed sample size study, right? Because if you want to win the win with a 62 subject. So this is one of the reason why for single arm, the futility analysis is sort of useful, but the context when Rich Simon proposed this is really in the context of there's a huge portfolio of drugs they want to screen, and by the cynical but realistic assumption that most of the drugs don't work, the futility design will actually save a lot of sample size in the long run. So this is very useful from drug screening viewpoint. But if you're talking to a company like a biotech that live and die by one drug, chances are you want to advise them to use a fixed fixed design. So adaptive design is good, but you need to know when to use it. So this is so the two observations that I made, and of course, it is really useful if you have multiple treatments. It's the third bullet point, and if you have concurrent control. And in some case, you can have a historical control. It really depends on the disease area and the availability of patients. But it is something that methods have been proposed how to do these kind of things. But the idea is that you need to specify the stopping criteria and know that the trade-off in the single arm study, but in the if you have multiple treatments, you can actually manage to reduce the maximum sample size as well as the average sample size. So this is very, very useful when you have multiple treatments. You definitely want to do equal analysis. So this is a no-brainer. Do it. Okay. Sorry for being strongly opinion about strategic design, but I think this is you need to appreciate sort of when to use it, when not to use it. How much time do you guys have? So, I want to pick up your and then 5 minutes for internal pilot, and then we can move to the small group. And so this is a phase 3. It doesn't have to be phase 3 setting, just to give some context for illustration. So let's say the study endpoint is a primary outcome for stroke, 4-point change in NINDS stroke scale, or modified ranking scale, let's say you at A90, so primary endpoint. And so if you want to do a sample size calculation for the analysis, we need to specify 2 values. Right? One is the placebo rate, the control, like what is the response rate, the placebo, and then the effect size. Effect size is really what the parameter of interest is. This is a number that should be determined from clinician. Not statistician has no role in doing that, except for the fact that they may want to look in the literature what constitutes a clinically meaningful difference. So that's a number that should be really coming from our clinical colleagues and with the help in the literature, and should be fixed throughout the study. We don't change what effect size we want to have in the study. On the other hand, in order to calculate sample size, we do need the placebo rate. We really don't really care too much about this placebo rate. This is what we call nuisance parameter in statistics, and it's nuisance because it's really annoying in the sense that we need to know it in order to get sample size, but this is something that we may not know. And that's where internal pilot comes in. And this table shows how much it affects the placebo rate affect the sample size required in this study. So assuming that we want to fix this effect size as 10 percentage points, so we want to see a 10 percentage point difference between treatment and placebo, and then if the placebo is 10%, we need about 200 subjects per arm. Placebo rate is 40, we need almost double the sample size. So it has a huge impact on the sample size. And the question is whether it's 10 or 40, we don't know. Well, hopefully we have some idea, but from what we've seen in the past, more often than not, we have placebo response rate that's better than expected. So that's often. And the consequences can be that if we're on the lower end, the consequence could be that the study is underpowered. If the placebo rate turns out to be better, if it's on the higher end of response rate, we may be overpowering the study if the placebo rate turns out to be better. So either way, either scenario is not ideal. And that's why we have internal pilot. And the idea is to do a pilot to estimate the placebo rate and then use that to calculate sample size. And this is a pilot. This is internal because we want to use the data we use to calculate sample size again at the final analysis. So it's not a pilot that you do external to the study that you're doing. So and there's some efficiency building because you're using that data again. So the example is simple illustrating point how to do it. So let's suppose that we again effect size 10 percentage point. That this is the number that we decide at the planning stage. We don't change it, and if we initially assume that the placebo rate is 10%, go back to the table. We know that about 200 patients per arm. That's the study that we need. But let's suppose that after 100 subjects, we're going to do a blinded estimation of the placebo rate, and out of the 100 subjects, we don't know which subjects which. We only know that 50 are in placebo, 50 are in treatment. We observed 35 responders. So the overall response rate is 35, right? And under the assumption that the effect size is 10 percentage point, we can actually estimate that the placebo rate is at 30%. And as a result of that, we can revise the sample size based on the 30% assumed placebo rate and raise it to 376 per arm total, meaning that you need to enroll another 326 in addition to 50 per arm. So this is a simple calculation, so should not be too complicated. So the nuance here is that the response rate is calculated under blinded, so under the assumed effect size. Few talking points is not a way, again, not a way to use the observed effect size to calculate sample size. There are methods for that, not recommended. And also in the previous illustration, I did not account for the variability in the estimated placebo rate based on you're estimating the placebo rate based on 100 subjects, which office has variability in it. You can actually build in some sort of to account for that by having some, you can either Bayesian or being conservative. And so, but there are various ways to do it, but it can be done. It was just an illustration. And the main issue at the end of the study is how do we analyze the data in the internal pilot. The answer is always it depends. And that's the answer, right? And,
You just run the regular analysis, right?
no, actually, this is actually this sometimes it can be done, and based on a lot of simulation studies, there's no inflation type of error. If your pilot n is large enough, if you have a pilot of 5 per arm, then it might not be a good idea. And so it's okay. So it's very important for you to determine this pilot sample size and then run simulation to see whether there's a severe increase in interval error. So that is usually okay, especially if you are thinking this in the context of earlier phase study. If you are thinking about pivotal study, maybe you want to do something more rigorous, which is what I call the weighted analysis. And so there's something in the literature, but forget about formula. So the idea is very straightforward. If you know how to do meta-analysis, you know how to do this. And so the idea is that you have a data in the pilot phase, you have data from the second stage, whose sample size is based on the pilot stage. If you view the data connect from these two stages as if they're from two independent studies, and then you just pull them together, use some whatever meta-analysis technique that you use, you get a better inference.
So you run independently, not once.
Right.
Okay. And then
You're not one contiguous like big thing, so you break them into two pieces. As a result of that, you may lose some power, but then you don't get penalized for type of error. So, but again, this is something that whether you need to do this is at least a lot of simulation, a lot of discussion whether this is important to have a really strict control of error.
And does it also, I can't recall, but does it matter if you do like an unblinded sample size re-estimation? This would definitely you want to consider. If you do a blinded sample size re-estimation, I thought this was less than an issue where you just could then do the final. Is that right?
Yeah. So because when you do unblinded, first of all, the key is that you never adjust the sample size based on the observed effect size. If you don't do that, even if you do unblinded sample size re-estimation based on what I call the nuisance parameter estimate, and you will be fine. The only concern about doing the sample size re-estimation based on unblinded estimate is that it's operational bias. It's not, the bias is not statistical, it's operational. Because you unblind the study and then, a lot of things can happen.
Can you go back one slide so can you go back one slide?
Sure.
Oh, okay, I got it, thank you.
But I think I might have lost you. You said sample size re-estimation is not based on the observed effect in the pilot data.
Right, so like in this example, the sample size readjustment is simply based on the estimate of the placebo rate, which is something that we really don't care much about as long as we can demonstrate 10 percentage point difference. So let's say that if you do a blinded estimation and you see that out of the 35 responders, 30 are from the treatment, 5 are from the placebo, then you say, well, so the difference is like 25% each point, then let's do a sample size based on the no, do not. So that's what.
Because investigators want to like take down their sample size or stop early, right? I mean,
Yeah, and also one thing about, yeah, that's a good point about reducing sample. There was also a discussion about like having a reduced sample size. FDA said no, don't do it.
Yeah.
So the one thing about internal pilot is that you want to have a small n to do the internal pilot and you increase from there. You don't want to reduce. FDA said no, so don't argue. And
Can you do it based like for variance too? If you have continuous outcome, you can estimate the variance in your, okay.
yeah, so you read my mind. That's another point. Perfect. And yeah, and this is sort of my last slide or second last slide. And so if you're curious, the idea of internal pilot appeared in the 40s. So from in the statistical literature, so the idea is not new from a statistical point. I think so the challenge to us is really how to bring it to life in a real clinical trial, right? I mean, it was proposed in 1940s. I don't know when the method actually first got used, but I think this is really a great time to use it, but we need to use it appropriately. So by doing that, meaning that again, adjustment based on observed effect size. There are methods out there, not a great idea in general. I'm not saying not to do it ever. It's a strong statement, but you need to be very careful when you actually do that. And some talking point in terms of number of different analysis, different methods, and like I do emphasize the last bullet point. All stopping rules and adaptations need to be pre-specified at the planning stage according to the FDA draft guidance on adaptive design. So this is very important. It doesn't mean that you can change in the middle, but whatever change occur will be something that is independent of the outcomes that is really observed during the study. So, so the more you specify in advance, the better. And this is the list of references that you can go through. Most of the material you can see is a textbook, but after you can get people something to guide you through the process. Okay, so moving over.
So when he was saying about estimating variability, would you use the entire sample to estimate the variability, or would you just restrict, or would you separate out placebo and treatment and estimate the variabilities? And
yeah, I would probably use full sample variance. So that if possible, always I prefer, unless there's strong reason to unblind, to do unblind sample size estimation, I definitely do a blind one. Yeah. It's not worth risking blind.
Let me ask you, one approach that is done in mega trials is to set the interim stopping rule at a p-value of 0.001 and then say it's such a tiny amount is being spent, you don't have to adjust at the end. So, or you make it 0.049 at the end.
Right.
Yeah, but you don't do any formal calculations. Is that something that statisticians would object to formally, or? There's some ethical concerns, but
Right, so that's a concern.
Oh, no. I guess I'm not familiar with that, so I'm wondering why they even do that.
because this comes out of the British tradition of mega trials, and the British don't want to stop trials. They want to get as much data as they can on everything. So they choose, but they feel obliged by everybody else to have a stopping rule, so they choose a stopping rule that they can't possibly stop them.
Yeah,
so O'Brien Fleming, I'm assuming with a 1 or 2 looks, would be very conservative, right? At
Right.
the first 2 looks.
Yeah.
If
So-
you did like a
It's
one
just
month
like a
or
one
trial.
look in the beginning,
Yeah.
then
Yeah.
it's,
Yeah.
as I was thinking, it was an O'Brien filming with
It would be
a
the
can
same,
of 1 or
same.
2.
Right?
Yeah.
That's what I'm
Yeah.
thinking.
Yeah, I really don't have any strong statistical concern, right? I mean, as long as there's not a statistical consideration, it's more ethical, right? But I do see the wisdom of having a do one conservative one at the beginning to make sure that like the trial has been run properly, because something can happen that give you some crazy result. So I think I do see wisdom of that. The debate is whether we want to sneak one right in the middle. So, but that's yeah. But I think I like that, because in a sense I like it. It's quite simple. But if something happened, then you do want to have some overshoot for it. mention
Thanks.
your name.